In this chapter, we will be studying radical and absolute value functions. In this lesson, we will be switching between entire and mixed radicals. We will also be adding and subtracting radicals.
Hi everybody. So in this first lesson, in this next chapter here, we're going to be looking at going from entire to mixed radicals, and probably vice versa just a little bit here. Then we're going to add and subtract radical expressions. Okay. Now, first of all, before we get into this, we are going to quickly review what we're talking about with radicals here. Remember, with a radical, we're talking about the root of a number. That's probably an expression that you're more familiar with. So, for example, right here, this is a radical because it's got that root symbol. And actually the root symbol consists of two parts. There's this, which is actually the root symbol. And then you've got the bar. And then the bar that goes with it, the bar always implies a set of brackets. Whatever the bar is over, okay, we consider whatever's underneath it to be within a set of brackets. And you should know that. That's something that's going to come up again and again, particularly when the issue becomes order of operations. You need to know that. Like when you see that bar, normally you think of division, and it implies brackets around the numerator, around the denominator. In this particular case here, it simply implies brackets underneath. Okay? Now, so this right here, though, one of the things you would have looked at in a previous course is the relationship between a radical and an exponent. So here we've got a power. The base of the power is x, and the exponent is a fraction, is an irrational expression, 1 over n. That is exactly the same as the nth root of x, okay? And we call x, in this case, the radicand. It's the part that's underneath or within the radical symbol, if you will. And then that n, the denominator in the exponent here, okay, becomes the root index. It tells us the kind of radical that we're working with, okay, what the power is. So, and if it's not written, you know what it is. Okay, if it's not written, if you've just got the square root of x, that means that the root index was 2. Typically, if we don't write it, it implies that that was a 2. And you're very, very comfortable with that. You've seen that before. Okay, now we can take this idea just one step further. If we throw an exponent in there, a numerator in there other than 1, that m, okay, that m becomes the exponent on the radicand, or if you will, you can put brackets around the whole thing and put that exponent on the whole root. Now I'm going to tell you right now, this is actually more useful to you. They are identical, but in terms of your ability to simplify, you're going to find that this one is probably far superior, or at least you're going to use this one way more often here. Okay, now I'm about to go through and we're going to take a look at some examples. So we're going to talk about simplifying. You should know that there are really two primary ways that people simplify radicals, and that's going to become an important part of this lesson as we go through it. I choose to use a tool that we were introduced to you in a previous course called prime factorization. Now, I freely admit the method that I'm choosing to use here is sort of slow compared to the other method. But the other method, and I will kind of hint at what that other method was in just a few minutes here, or is in a few minutes here. But the other method is quicker, but limited in terms of the kinds of roots that you can analyze. But the method I'm about to show you right here, it just works. It works. It doesn't matter what the root index is, how complicated it gets. It just always works. That's why I love it. So to start off with here, we're going to evaluate each of these next powers here by converting it first of all to radical form and then simplifying. So for example, the 32 to the 1/5, what that means is that is the 5th root of 32. Okay, 5 in the denominator, 1 is the exponent. Now, what I recommend that people do is we take that 32 and we're going to break that down into its prime factors. Now this is a skill that you should have mastered in a previous course here. So 32, think about it, the first prime factor that I would test in there is 2, and I take 32 divided by 2, I'm left with 16. 16 divided by 2 leaves me with 8. 8 divided by 2 leaves me with 4. 4 divided by 2 leaves me with a 2 here. So 32 is actually 2 times 2 times 2 times 2 times. There are 5 2's here. Okay? Now think about what this root is doing here. This 5th root is saying that I'm supposed to take groups of 5 every group of 5 prime factors becomes a single value out front of the radical. Now in this case, all I had under the radical was 5 2's, so that means every one of those things got pulled out as this single 2. The 5th root of 32 is in fact just 2. Okay. This one right here, -8 is the base of that power, which means that this is going to be the cube root, and the radicand here is -8. Now this works out just fine for me with a negative underneath a cube root. If the negative is under a cube root or a 5th root or a 7th root, what I'm going to do with that negative is simply pull it out. Now, if this was a square root or a 4th root or a 6th root, that's a little different. Because of the even the root index, unless we're willing to work with imaginary numbers, there is no real root that we can take of a negative number there. So that would be kind of a dead end for us at this point. Now, here though, because my root index is odd, I could, for example, break this down into 3 -1s multiplied by them together here. Honestly, I think the easier thing to do here is just to realize that if this is odd, I can just pull the negative right out here and just deal with that first. Now 8 is divisible by 2, gives me 4, which is divisible by 2, which leaves me with 2 here. So 8 is just 2 times 2 times 2. I'm looking for groups of 3 of any kind of factor there. So again, there is that group of 3 2's there, so I yank out a representative of that group of 3. And then that actually took everything out of the radical. I'm done. The cube root of -8 is -2. Over here, again, I'm going to convert this 16 to the 3/2 into a radical. So this is going to be the square root of 16. Now, here's what I was talking about before here. I can put that cube in 2 different locations. I can either put it right on the 16 here, or I can put brackets around the whole thing and put it outside. Now, if I put it inside here, then I need to evaluate 16 cubed first, because remember that bar implies a set of brackets. So I'd have to do what's inside first. I don't know what 16 cubed is, and I'm not particularly sure I am willing to do that kind of work here. But if I put brackets around that, and then cube it at the end here, I do know what the square root of 16 is. In fact, I don't even have to write that as a set of prime factors. I mean, I certainly could, and in fact, maybe I would. Maybe I will here. But I already know that 16, the square root of 16 is going to be 4. But just to show you how this works again here, 16 divided by 2 is 8, divided by 2 is 4, divided by 2 is 2. I have got 2 groups of 2 factors. So I'm going to pull a 2 out for that one. I'm going to pull a 2 out for that one. Okay, they are multiplied together. I haven't even dealt with the cube yet. I'm still just trying to deal with the square root. I pulled out a 2, I pulled out another 2, so 2 times 2 is 4. Oh, I'm getting all sorts of crazy shadows here. Hold on. And that's going to be 4 cubed, and 4 cubed is 64. So 16 to the 3/2 is going to be equivalent to 64. Okay? Anyway, I hope this is ringing bells here. This is stuff that you should have looked at in an earlier course. So just, again, a little bit of vocabulary that you should know here. An entire radical, or a pure radical, sometimes they're called pure radicals. That occurs when all of the numbers or letters are under the radical sign. Okay, so you're looking at stuff that looks like this. There's basically, the only coefficient here, if you're going to think about it that way, the only coefficient is 1. Okay, everything else is inside. Mixed radicals, on the other hand, are what you might call simplified. Okay? In other words, we have yanked out something inside there, and we're now, it's created a coefficient for us. So for example, 2 root 3, a root b, 3 multiplied by the 4th root of 2. Those are all what we would call mixed radicals. And in most cases, as long as what's underneath the radical symbol, as long as the radicand is as simple as it's going to get. In other words, like for example, for these guys here, I've pulled out all of the pairs of roots that I can, because these are square roots. I've pulled out as many as I can. Okay, here I've pulled out as many groups of 4 as I could. And what I'm left with is as simple as it's going to get. Then we would consider that simplified. All right, now, really quickly, I just want to talk about this other method here. There is another way of breaking down radicals, okay? But it requires that you're somewhat comfortable with perfect squares, perfect cubes, perfect fourth powers, perfect fifth powers, okay? Which is why on this particular page here, in the notebook that we're using, we've got these things listed off here. And let me show you how this works. I'll just kind of pull up an example here. Let me think of one here. Okay, let's say for example that I was to ask you what the square root of 75 was in reduced form. What I would need you to do here is to look at this, realize that I'm asking you for a square root. So then you would think, okay, what's the largest perfect square that is a factor of 75? So you got to start thinking about your numbers here, and 75 isn't divisible by 2, but it is divisible by 3. Okay, and so if you do that, that's going to leave you with 3 times 25. Well, I recognize that 25 is a perfect square. So this becomes root 3 times root 25. And I know that the square root of 25 is 5. And now, just to make this look better, I'll write that 5 out front. And it's 5 multiplied by the square root of 3. That would be the simplified form of root 75. Okay? And that works great. It totally works great. But that requires that you need to be very comfortable with your perfect squares, okay? Now, and perfect cubes and so on and so forth. Now, where this might get problematic is sometimes people look at this and they say, well, wait a minute, what about 64? Isn't 64 the largest perfect square? And see, this is the problem. This is where this one gets frustrating here, is because 64 is the largest perfect square that's less than 75, okay? But it's not a factor of 75, and I'm looking for the largest perfect square that's a factor. So not only do you have to be familiar with your perfect squares, you got to be familiar enough with these numbers here that you can identify what are the factors of these things. And for the most part, if you're talking about perfect squares, usually the numbers that we're working with aren't terribly big, but it doesn't require a very big number when I ask you for the perfect fourth root, or I ask you to simplify something that's got a fourth root. It doesn't take me long to throw numbers down there that are going to be really difficult to work with. This is why I like the idea of breaking things down into prime factors. If you break them down into prime factors, it doesn't matter what the root index is. It makes no difference what it is. If you've broken it down into prime factors, you're just going to grab that many factors and yank them out. Okay, it makes it a little bit easier. It's a little bit slower, but I think for the most part it's a little bit easier. Anyway, let's take a look at some examples. All right, so this question that we're going to work through here says express each as a mixed radical, which basically means here, if I could do this here, means simplified form. Okay? We want to reduce these as far as we can. So the square root of 20 here, and I'm going to model the method that I think is probably more universally applicable here, universally or easily applicable. 20 is divided by 2, gives me 10, which is divided by 2, which gives me 5 here. I'm looking for a square root. Okay, if it's not written there, it's a 2, which means I'm looking for pairs of factors inside there. Okay, so there's a pair of 2's right there, so the 2 comes out, a 1, 2 comes out as a representative of that, and I'm left with the root 5 in there. Okay, so now if you're wondering why this is asking for pairs here, you got to think about what we're doing here. When I'm asking for the square root, essentially what I'm doing is I've given you a square here, and I'm saying that this area is 20, and I want to know what the side length is. Okay, well when I multiply these together to get 20, there was a 2 multiplied by something, a 2 multiplied by something here. 2 times this other something squared gave me that 20 here. That's what I want you to do. I want you to break it down and figure out what the length of the side is. So those two 2's, one of those goes to like the length, one of them goes to the width. So together, what's the side length? Well, there was a 2 in there for sure, and then there was the square root of 5. I hope that helps clarify what we're doing here. Anyway, cube root of a cubed. Now, this question really is representative of what we're trying to accomplish in this particular course at this level. Now, I'm going to do this 2 different ways here. The cube root of a cubed. Now, sorry, not the cube root, the square root. The root index here is 2. What I might do here is, because this is a cubed, I might actually write out that a 3 times. And then because it's a square root that I'm dealing with, that pair of a's becomes a single a outside the square root, and then there was an a left over that I couldn't do anything with. So those 2 a's become that a multiplied by the square root of that remaining a. Now, that is easy enough to do because the exponent that I'm working with here is quite small, okay? But it's not going to take long before those numbers are going to get unreasonably large. Okay, like if I had made this 23, then I'm going to write out 23 a's there. I'm not going to do that. So I want you to see another way that we could do this here. It is essentially accomplishing the exact same goal. It's just doing it without me writing this all out here. Essentially what I'm doing to that 3 is I'm dividing it by 2. I'm dividing it into groups of 2 because of the root index. I've got one group of 2, so this is like a to the 1, with a remainder of 1 left over. So 3 divided by 2 is 1 with a remainder of 1 on the inside. And that's how we're going to think that through. Now you're going to see me do this a few more times here, so hopefully this will make sense in a bit. Over with this next one, we're looking at the cube root of 40. Again, I think the smarter thing to do here is to simply break 40 down into its prime factors. It's divisible by 2, that gives us 20. 20 is divisible by 2, okay, that gives us 10. It's divisible by 2, and that gives us 5 at the end there. And those are my prime factors. It's a cube root, so I'm looking for a triplet. And again, you might think of this as being length times width times height. Okay, so the length of one side is definitely going to have a factor of 2 in it, but there was that 5 that I wasn't able, there was a 5 there that I wasn't able to break it apart. So the best that I can say here is that the length of a side here is going to be 2 multiplied by the cube root of 5, whatever that turns out to be. But that is about as simple as I can write that without going to the calculator to get a decimal version of that number. The 4th root of 48. Okay, 4th root of 48. Now again, see here, I could do this using that method of finding, well, what's the largest perfect 4th power that's a factor of 48? But then I got to know what those are. Okay, I don't know what those are. I don't know. I mean, I'm assuming it's going to be 2 to something here. But the other thing that I can do here is I can see quite clearly that that's divisible by 2. Okay, and if I divide 48 by 2, I'm going to get 2 times 24. Well, 24 is divisible by 2. Gives me 12. 12 is divisible by 2. Gets me 6. 6 is divisible by 2, and I get 3. So 2 times 2 times 2 times 2 times 3 gets me 48. I'm trying to find the 4th root, so I'm looking for a group of 4 of the exact same factor, and there they are. There's my 2's. So to represent those 4 2's, which represent your length times width times height times whatever the 4th dimension is, okay, I'm just going to put a 2 up front there. And then what I was left with was the 4th root of that 3 that I couldn't do anything with, so I just leave it inside the radical. All right, over here. Okay, now this one's got a lot going on here, and I like it. Okay, it's a cube root, and I see that it's a cube root of a negative, so the very first thing I'm going to do is I'm going to yank that negative out. I can do that if it's odds here. There are other ways that I could kind of noodle this through, think about it here, but you know what, that's just the easiest thing to do. If it's an odd root index, the negative is going to pop out. If it's an odd root index, I could put the negative back in. If it was an even root index, I'm not going to get real results if I try to deal with the negative on the inside. And if it's an even root and there's a negative on the outside, then I'm not going to be able to push it back in. Like the negative and the even number, they don't work well together. Okay? But here, this is fine here. Now, this is going to be the cube root. Okay, so 48. We already dealt with 48. It was 2 times 2 times 2 times 2 times 3. And then I had the variables here. Now, I could have written out 3 x's and 7 y's, but I'm not going to do that. What I'm going to do here is I've got 4 2's, so I'm going to have a 2 out front here. Now, 3, I'm going to take the exponent on the x because this is going to tell me how many x's are in here. And I'm going to divide that into groups of 3. Now, 3 divided by 3 is 1 with a remainder of 0. There is nothing left over under that radical. So I've got this radical here Okay, there's definitely a 3 left over, but there's no x. I pulled them all out here. Now take a look at the y here. The exponent is 7. There are 7 y's underneath this radical here. I'm going to divide it into groups of 3. 7 divided by 3 is going to be 2, but there's going to be a remainder of 1 left over. There's, okay, 1 additional y left over. Now, because the exponent is 1, I didn't have to write it in both those cases there, but if it helps, by all means do it. Okay, it's not wrong to do that, it's just redundant, it's not necessary. So that one simplifies down to that expression right there. Okay, now let's focus specifically on these variables here. Remember that if the radical isn't written, okay, or the root index isn't written, I should say, that's going to be a 2. So the exponent here is 5. There are 5 a's here. I'm looking to break that up into groups of 2. So 5 divided by 2 is going to be 2 with a remainder of 1. And I'm not going to write it in this case. Then I look at the 9. 9, okay, there are 9 b's here. 9 divided by 2 is going to be 4. And again, with a remainder of 1. So the square root of a to the 5th, b to the 9th will be a squared b to the 4th multiplied by the square root of ab. There was this little bit left over that I wasn't able to follow my little pattern for, breaking it into groups of 2. That's where I leave it. Don't know what to do with those guys yet. Okay, another one here. So I'm going to deal with my coefficient here of the radicand here. So 24 is divisible by 2, gets me 12, which is divisible by 2, it gives me 6, which is divisible by 2, gets me 3. And instead of writing out 5 b's, I'll just write it as b to the 5th. I'm looking for a group of 3 because of the root index, so I'm going to put a single 2 out front. And then b divided in groups of 3. Well, that's going to be just 1. And then I look what's left inside here. Well, there's a 3 left inside the radical. And then 5 divided by 3 was 1 with a remainder of 2. So this will be 2b multiplied by the cube root of 3b squared. Okay, the square root of 20x to the 4th y to the 13. Okay, remember that if the root index isn't written, it's a 2. First of all, I want to deal with the numerical coefficient here. So 20 divided by 2 is 10, divided by 2 is 5, x to the 4th, y to the 13. So there's a pair of 2's. I'll write that 2 out front to represent that pair. And then, okay, x to the 4th, the 4 divided by 2 is going to be x squared with no remainder. 4 divided by 2 is just 2 with no remainder. So the x's are gone from underneath the radical. 13 divided by 2 is going to be 6. And then there's going to be this remainder of 1. Okay, there's 1 y left over. So there 5 was left over from simplifying that numerical coefficient, and then the 1 single y was left over after I divided that 13 by the 2. All right, and now finally, the 4th root of 32a to the 5th. Now, beyond a certain point, you could start dealing with the numerical coefficients the same way you're dealing with the variables here. Okay, yeah, but I'm going to just keep working at it the way I have been, because we talked to you about prime factorization. And I really do want you all to be very comfortable with prime factorization. Okay, you can use this idea of a prime factorization in so many different ways here. You can actually use it to help you, and I know this is going to sound weird, to help you multiply more quickly by knowing how to reduce numbers down to their prime factors. The more comfortable you are with that, the easier you're going to find it to multiply later on. And you'll very likely see some examples of that coming up in the next few lessons. So 32 is 2 times 2 times 2 times 2 times 2. Okay, we've already actually worked with that one. I'm looking for the 4th root, so I'm looking for a group of 4. Unfortunately, that doesn't deal with all of them. There's still a 2 left over. So there will be a 2 out front. 5 divided by 4 is going to be a to the 1. And now I got to look at what's left over. There's going to be a 2 left over and another a, one final little a left over. So 2a multiplied by the 4th root of 2a.
Now we will switch from mixed radicals to entire radicals.
Okay, now we're going to go from mixed to entire radicals or mixed to pure radicals. And actually, this one here, this is going to go by pretty quick because this is actually fairly straightforward, I think. Especially if you're following what I was just doing to simplify radicals, all I'm wanting to do is go backwards. So, for example, if I had a fourth root, I was looking for groups of 4 factors and I pulled out a single representative. Well, now when I take that representative and plug it back in, if the root index is 4, I'm simply going to take whatever that is, and there will be four of them inside there. Whoops. So for example, when we have 5 multiplied by the square root of 3, what I'm going to do here is simply make sure that I've got 5 there twice, and then I'll multiply it by that radicand, so the root of 75. Okay, over here, because the root index is 3, I'm going to take that negative 4x. Now here again, because that's odd, I can keep the negative with me. Okay, so I'm going to move that whole thing inside there, and this will become negative 4x cubed. Okay, 4x, and that's all cubed. And it's not just the 4 cubed, or it's not just the x cubed, I should say. It's that whole thing here. And then I'll multiply it by that 7x squared here. Now, just so that we've got this as a comparison here, let's say that this was negative 4x, and this was now the, let's say it was the square root of 7x squared. Okay, I need you to understand this very, very clearly, that the negative and the even root index here don't play well with each other. If you follow what I just did here, you're going to be very tempted to do this. Make this the square root of negative 4x squared multiplied by 7x squared. And this is wrong. What you would be tempted to do here is make this the square root of, okay, well, 4 squared is going to be 16, multiplied by 7 is going to be 112, so it'll be 112. The negative squared is positive, and then you get x squared, so x to the 4th here. But this is incorrect, okay? And the reason why it's incorrect is because when I convert from one form to the other, I shouldn't actually be changing the value of the expression or what it represents. There should be no change here, okay? 5 multiplied by the square root of 3 is exactly the same as the square root of 75. These are just 2 different ways of representing the exact same value. I have done nothing, okay? If I was to plug in a very specific value for x into this expression and to this expression right here, and plug it into my calculator, I would get the exact same decimal representation at the end, because these are identical to each other. There's no difference. But here, I have changed it. This up here is negative, this down here is positive. So I need you to understand that if you're doing this with a square root, or a 4th root, or 6th root, or whatever, if the coefficient is negative, that negative cannot be moved inside, because if this expression is negative, I need the final expression to also be negative so that they're equal to each other. Okay, please don't move that negative in. That would be inappropriate. Okay, let's take a look at some examples. Okay, so the question is asking us to convert each of these into from mixed radicals to entire radicals. So I just have to recognize that that's a square root, meaning that that coefficient is going to show up twice. And 2 times 2 is 4 times 3 is 12. So 2 root 3 is exactly the same as the square root of 12. Here, this is, again, it's a square root, so this will be the square root of 5b times 5b, and then what was left over in there, or what was in there to begin with, the radical, was 3b squared. 5 times 3 is 75. b times b squared will be b to the 4th. And these 2 expressions are equal. Okay, now we're looking at a 4th root here, and this is what I was referring to just a couple minutes ago here. That's a 4th root, but the coefficient here is negative. If I try to move that negative inside by taking this, this expression here to the 4th power, I'm going to lose that negative. So that negative, it has to be there, so I have to leave it out front here. So this will be multiplied by the 4th root of 2x. Now, I'm getting kind of lazy here. I don't want to write this out 4 times, so I'm just going to write this to the 4th power multiplied by 6xy cubed. Okay, so this will be the negative 4th root of, okay, well, 2 to the 4th is going to be 16 times 6. It's going to give us 96. X to the 4 will be x to the 4th. Multiplied by x will give us x to the 5th. And then I didn't bring in any new y's, so this is simply going to stay as y cubed. So the negative 4th root of 96x to the 5th y cubed. Okay. Now, this is a square root, so it's going to remain a square root. 4m to the 5th n, and we'll square that, multiplied by 3m. Okay, 16, okay, because 4 squared is going to be 16, multiplied by 3 will give us 48. M to the 5th squared, now I got to be careful about that. M to the 5th, when I square this, I'm not squaring the exponent. When you square a power, you multiply the exponents. This will be m to the 10th. And then there's an additional m out here, and when you multiply them, you're going to add. So this will be m to the, m to the 11th. And then here I've got n squared. There's no other factor of n there. I hope that makes sense with the m there. M to the 5th squared. I multiply powers. A power of a power, you multiply the exponents, and then I'm multiplying it by this power of m, m to the 1, so then you would add that final exponent on there. Okay. The cube root. So I'm going to take that expression here, and when I shove that inside there, I'm going to have to cube it to get it inside. So this is going to remain the cube root. Now 2 cubed is 8 times 4 is 32. K squared cubed. Now when you got a power of a power here, remember we multiply the exponent, so this will be k to the 6th multiplied by k to the 1, and then I add the power, so k to the 7. This is going through questions like this is really good practice of the exponent laws. Okay, and now finally over here, and actually this question is good for another completely different reason. Look at the way this is written here. It would be very tempting for people to make a very predictable mistake, by the way. This is the cube root. Okay, so I'm going to take 7x cubed y, and I'm going to have to cube that to put it inside here. Now notice it's not y cubed that I got to put in here. That 3 is not the exponent on the y. Okay, it's part of the cube root. This is actually y to the 1. But a lot of people, when they read this really quickly here, they'll see that as both the cube root and the power of the y. Okay, and again, it's not because you have a misunderstanding. It's just because you're in a hurry. You're thinking kind of ahead of your hand, if you will. You're writing stuff out, and your brain is already like a step ahead of your hand, and so you start writing the wrong things down there. Just something to be aware of, so that you try not to make those mistakes. Okay, so we've got 7 cubed. Okay, and then we're going to multiply that by the 3 that was already inside there. So this will be the cube root of 1029. And then I'm going to have x cubed cubed. Okay, that's going to be x to the 9th. Multiplied by x to the 5th will be x to the 14. Now it's interesting. This was not even the fully simplified form of this. Okay, before we started to convert this back to an entire radical. And then this will be y cubed. Okay, multiplied by y to the 4th will be y to the 7th. All right, there you go. Just a little bit of practice converting from mixed radicals to entire or pure radicals.
Now we will add and subtract radicals.
Okay, now to finish off this lesson, we're going to take a look at adding and subtracting radicals. And this is a very, very simple thing to do if you've mastered the idea of simplifying here, okay? So in order to add and subtract radicals, they have to have the same radicand and the same root index. In other words, they have to be what we call like radicals. Okay? The radical portion of the expression must be identical. The exact same radicals. So you see the square root and the square root, it's the square root of 2 and the square root of 2. and you only add or subtract the numbers in front, or the coefficients, and you leave the radical alone. Now, I think I can help a lot of people who are tempted to do this incorrectly here. I think the best thing that people can do to approach a problem like this and to do it correctly is to speak this thing correctly, to say it right. Some of you do a disservice, and you do the same thing when you're working with fractions, by the way. Understanding how to work with fractions primarily is about understanding how to speak the question, how to talk the lingo correctly. If you say those things correctly, your brain will start to process this correctly. Don't think of this as 6 multiplied by the square root of 2 minus 4 multiplied by the square root of 2 and say, what does that equal? Ay, ay, ay. You're making that harder on yourself. See, you don't know what the square root of 2 is. No, don't go to your calculator. Don't go to your calculator and say, yes, I do. I know the square root of 2. It's that. Yeah, I can do that too. But even that's a rounded version of it. Root 2 is an irrational number. That decimal goes on forever. This isn't even exactly the square root of 2. This is an approximation to whatever decimal place that is. So you don't know what the square root of 2 is. Okay? That's an unknown. This is very similar in structure to 6x minus 4x. Now, see, here's an expression right here, and I don't want you saying this, 6 multiplied by x, subtract 4 multiplied by x. You're making that harder. This is 6 root 2's minus 4 root 2's is how many root 2's? Well, wow, and this, in fact, this was even done wrong. That's hilarious. That's a typo here. 6 root 2's minus 4 root 2's is 2 root 2's. Okay? 6x's minus 4x's is 2x's. Now, usually it makes sense with x's, but as soon as we transfer over and start talking about radicals, that's where people start to make goofy and yet very predictable mistakes, by the way. If you're someone who you kind of know, I'm probably going to struggle with this, I'm going to do this kind of weird here. It's a matter about training your brain to think this thing through correctly. And don't worry about the struggles that you're having with here. This just takes a little bit of practice. You'll get through it. That's not a problem here. Just remember to say this correctly here. 6 root 2's minus 4 root 2's. How many root 2's have I got? 2 root 2's. Okay? I'm not asking you to go beyond that. Okay? I'm not asking you to go beyond. I'm not asking you to multiply 2 by the root 2. Just write down that that's what that would look like at the end. Okay, so let's run through some examples where we're adding and subtracting radicals here. All right, so right away, take a look at what we got here. I've got 2 root 3's, and I'm going to add 4 root 3's. Again, don't try to think of that like, what the heck? I can't do this unless I know what the root 3 is. Yeah, you can. Yeah, you can. I've got 2 of them here, and I'm adding 4 of them, which means I've got 6 root 3's total. Don't worry about going beyond that. This is all I want you to do. Identify the number of root 3's you've got. The only other work that I would expect you to do in a question similar to this would be to simplify the radical down if possible. That's it. So, and just as way of an example here, I've got 18 root 27's and I want to subtract 25 root 75's. Well, those aren't even the same. Like, I don't know what the square root of 27 is. And I don't know what the square root of 75 is. I do, however, know that they're not the same number. This isn't the same thing. This is like saying 18x's minus 25y's. Well, how am I supposed to subtract those? I have no idea how you're supposed to do that. They're different objects. Okay? But I can simplify those, okay, a little bit. 27, well, 27 is not divisible by 2. It is divisible by 3. Which gets me 9, and 9 is also divisible by 3, so I get 3 times 3 times 3. 75 is not divisible by 2. It is, however, divisible by 3, which gets me 25. 25 is not divisible by 3 anymore, so I move to my next prime number, and 25 is going to be 5 times 5. These are both square roots, so I'm looking for pairs of factors. So I'm going to take a pair. That pair of 3's is going to become a single 3 out front. Now, bear in mind that these are all multiplied together. So when I take that 3 out, okay, that's part of the radical. That was being multiplied by 18. So 18 times that 3 will be 54. And I can't do anything with that remaining root 3. I just can't. Over here, there were a pair of 5s, so that's going to come out. And I'm going to multiply that by the 25 that was left over here. And that's actually going to get me 125. And again, there's a root 3 here. Now look, after simplifying, now there's a connection between these two. I still don't know what the square root of 3 is. But I do know that that root 3 and that root 3 are the exact same thing. So I've got 54 root 3's here, and I'm subtracting 125 root 3's here. Okay, 54 minus 125 is negative 71 are root 3's. That's how many root 3's I've got left over. Don't go beyond that point. There's no reason to. So now we're just going to do a little bit more of the same thing. So 2 root 18 plus 9 root 7 minus root 63. Okay, well, I mean, none of those are the same here. So the first thing I got to do here is try to simplify this. 18 is divisible by 2, gives me a 9, which can be broken down into 3 times 3. 7 here is a prime factor. That's it. That's as nice as that's going to get. Well, that's interesting because there's no connection between those two then. Okay, there is no 7 in here. There's no 2's and 3's in here. That's interesting. Root 63. Okay, well, okay, when I look at 63, I know that 63 is 9 times 7, and 9 is 3 times 3. So this is going to become 3 times 3 times 7 here. I will simplify this by taking that pair of 3's to pull out a representative of that out front, multiply them together to get 6 root, and there was a 2 left over. I've got a 9 root 7 as my second term. Those aren't even related. Here I can pull out a 3, and I've still got a root 7 here. So look what this is saying. 6 root 2's plus 9 root 7's minus 3 root 7's. Well, okay, this one really does stand alone here. So 9 root 7's minus 3 root 7's. Let's just deal with that first. That's going to be 6 root 7's. Now you might look at this and say, well, wait a minute, yeah, there's a 6, they're related because of the 6 is there. Yeah, but remember that 6 and that 6 right here are telling us how many of these radicals we've got. But these radicals are not related to each other. I cannot add root 2's and root 7's together. They are completely different. Okay, so that turns out that is the end of it. I know what it's like. I've seen students go through this. I've struggled with this myself here. Sometimes it's very hard in math to know when you're done. Right now, we are done with this question. I cannot go any further. And I know it's kind of weird because I've got 2 terms there and there's a really strong desire for people to go, I want to simplify this to one little blip of a number here. But I really can't until I go to the calculator to get that decimal number, and I don't want you doing that. Okay, this is an exact value. Okay, this is an exact value. If you go to the calculator will give you a precise value to a certain number of decimal spots, but not exact. This is perfect. The calculator cannot provide enough decimal places to get these 2 radicals correct. This is exact. In order for me to do some sort of, to do the addition here, just think about what your order of operations would be. You would need to multiply those together and then add order of operations. But because I don't know exactly to an infinite precision what the root of 2 is or what the root of 7 is, I can't actually add those together and get an exact value. I'm done. Okay? It takes some practice to get used to how to recognize that. So don't get mad, don't get angry. I understand that sometimes for some of you there's going to be opportunity here to get frustrated. Just kind of keep muscling through this. Experience will start to show you when you're done. Okay, 2 cube root 16 plus 3 cube root of 54. Again, those are very different radicals here. So I'm going to try to simplify first. So 16 is 2 times 2 times 2 times 2. Okay. 54, cube root. Okay, 54 is divisible by 2, and that gives me 27, and I've already played with that, and I know that 27 is 3 times 3 times 3. There is a group of 3 2s here and a group of 3 3s here. I'll pull out a representative. There was already a 2 out front, so you multiply those together. So this is 4 times the cube root of 2. Those 3's get multiplied by the 3 that's out front, so it's going to be 9 multiplied by the cube root of 2. And so again, here we've got, I've got 4 cube roots of 2 plus 9 cube roots of 2. Okay, so I just have to identify how many cube roots of 2 I've got total. Well, 4 and 9 is going to be 13 cube roots of 2. So that's what that expression would simplify down to. All right, let's take a look at a long one, an ugly one here. Okie dokie. Got a lot going on here. You've got some fractions here. Now, you've probably had enough experience to know that sometimes there are opportunities where you can multiply through by the common denominator to get rid of the fractions. But you can't do that here. The reason you can't do that here is because this is just an expression. Okay? There's just an expression. If this had an equal sign, if this was an equation, then you could multiply both sides of the equation by that 5 to get rid of the denominator here. But I can't do that here. So I just got to simplify this as much as I can. Now, notice that I've got a cube root and I've got a negative in there. I'm just going to yank that negative out first. And then the cube root of 64. Well, 64 is 2 times 32. And I've already played with 32 enough to know that that's 1, 2, 3, 4, 5. There's a bunch of 2's in 32. Dividing by 5 is the same as multiplying by 1/5, and I know for some of you that's going to come across as something weird here, but dividing by 5 is the same as multiplying by 1/5 of something is the same as dividing by 5. Just kind of think that through there. That should make sense to you in a second or two here. This will be the cube root of, okay, 512. Okay, now 512 is going to be 2 times 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 2. That's a big one. With a W cubed there. Oy, oy, oy. This is gonna run off my my little space here. That's okay. This will clean up in a second. Anyway, let's keep going here. Then I've got this minus 2/5. 50. Thankfully, 50 is nowhere near as bad. This is going to be 2 times 5 with a W in there. And then at the end here, well, 2W. Actually, turns out that is as nice as that's going to get. In that case there, my 2 and my W are both my quote-unquote prime factors. Can't break that down any further. Oh, good. Now, I went through this big messy step. Now this is going to clean up real nicely here. I've got a group of 3 2's there and a group of 3 2's there, which means I'm going to pull out a 2 and a 2. So this will be negative 4W over 5. And then because there was nothing left under the cube root, I'm done. Here, again, I'm looking for a cube root, so groups of 3. So there's a group of 3, there's a group of 3, there's a group of 3. So this is going to be 2 times 2 times 2, so it's going to be 8/5. And then there was 3 W's here, W cubed. Divided by 3 is going to be just W. Awesome. Next, I had a pair of 5's there, so the pair of 5's come out. Now watch, there was a 5 in the denominator, so I'm going to pull out a 5. That is going to be in the numerator. This is all like over 1 in the numerator, so that 5 is going to stay in the numerator. That's going to cancel with that 5 down there. So not only do I simplify the radical, turns out I simplify the fraction as well. That's wonderful. So this will be minus 2 root, and this has a 2W left over in there. And then at the very end of this expression, I had a negative 4 root 2W that I couldn't do anything with. So here we go. Now we're going to put this all together. These are like terms because the variable portions of them are identical. So negative 4W over 5 plus 8W over 5. I'm simply going to add the numerators together. And this is like negative 4W's plus 8W's all over 5. Okay, or actually, a better way to think about that, maybe I should take the opportunity to talk about this. Dealing with fractions here, you might want to think of this as negative 4 w over 5 plus 8 w over 5. And I am totally free to write it in that way here because these terms are all multiplied and divided together. Order isn't really an issue there, so I can write those however I want. So this is negative 4 w fifths, or fifths of w, plus 8 fifths of w. How many fifths of w am I left with? Well, it's going to be 4 fifths of w. Okay, or if you want to think of it, if you really got to think of it in terms of like the algebraic approach, you're just going to add the numerators together. So negative 4w plus 8w is going to be 4w. So I'll maybe come down here and do that, if that's how you got to think that through here. This should be a little bit easier. I've got negative 2 root 2w's minus 4 root 2w's. It's going to be negative 6 root 2w's. And there's really not much I can do to fix that or make that any better. That's how that's going to work. 4w over 5 minus 6 root 2w. Okay, now finally this last one here. I got to simplify this first before I can put those together. We have already played with 32. That's going to be 2 times 2 times 2 times 2 times 2. A squared, whoops, push too hard on that. B cubed, whoops, sorry, I don't know why I put that negative sign underneath there. Negative sign should be in between. AB. Now root 98 is going to be 2 times 49, which is 7 times 7, and then there's a b left over. So these are both square roots, so I'm looking for pairs of factors. So I pull out a 2, I pull out another 2, that's going to be 4. Divide the exponent by 2, so that'll give me a 1 with a remainder of nothing. 3 divided by 2 is going to be 1 with a remainder of, okay, there's a 2 left over, and there will be a b to the 1 left over there. Minus, I can pull a 7 out, 7, AB, and there was nothing else I could simplify inside that radical. Okay, I just had a 2 and a b left over. But this works out great. I've got 4 AB root 2b's, and I'm going to subtract 7 AB root 2b's. The variable portions and the radical portions all work together. And because they're exactly the same, I don't know what they are, by the way. I have no idea what they represent, what those numbers are that they're supposed to represent. Not a clue. But I do know that if I've got 4 of them here and I take 7 of them away, I'm going to have negative 3, whatever that is, left over. No idea what it is, but I know this much I do know. If I've got 4 of them here and I take 7 away, I'm going to be left with negative 3 AB root 2b's. That's it. Man, I hope that helps clarify this. I know this can sometimes be a chapter that causes a little bit of anxiety. Please just slow and steady, continue to practice this, and anytime you run into difficulties, please go ask your teacher. They would really appreciate it if you did. Okay, we do want to help you through this.